Hey everybody, we are going to go into a new chapter for this week. It's going to be chapter 11. As you can see, the do now to this lesson would have been just reflecting on your previous test, but hey, you guys didn't take that. So this new concept that you guys are going to learn, and I'm actually really excited to be able to share it with you guys, it's called a limit. Now, on my flip chart, you can actually see that I've referenced a GeoGebra thing that I've created. I can't really show that to you because of how my computer is oriented. So instead, I'll try to describe it to you. So I made a rectangle with a perimeter of 24 units, and really what this program does is it shows you the rectangle, and I can change the size of it. The perimeter stays static, so if I make this side shorter, this side gets longer to maintain that constant perimeter. And you can see, like, what we look for is we look for the best area on here. All right, so this is really a concept that you guys have learned a long time ago, where we want to maximize the area of this rectangle. What is the maximum area? We can write it as something called a limit. But first we need to do a little bit of math, and to do that we're going to just take some of this stuff. We got the perimeter is equal to 2L plus 2W, right? Well, we know that's equal to 24 because of this information from the setup to the problem, right? So we can take this and we can solve that for, let's just solve it for one of the variables. I'm going to solve it for L just because that's the harder one to distinguish. Like, that's just a letter that's really hard to distinguish. So I mean, here we can have 2L is equal to, if I subtract 2W from both sides, I'd get 24 minus 2W, divide by 2, I'd get L is equal to 24 divided by 2 is 12, minus 2 divided by 2, just W, right? All right, so the next thing that I can do, I can see that my area is equal to length times width, right? So length times width, well, this time we know the length is 12 minus W. We get 12 minus W times W. Do a little bit of fancy math, you know, the distributive property, and we can make this into 12W minus W squared. Now, if we were able to play around with GeoGebra, you would actually see that we can get the biggest area when we make this into a square so that each side is a length of 6. We don't really need to worry about this illustration. What we really need to worry about here is something that we call a limit. So this is the first time you're seeing it. So I write it as LIM, and I like to put it in cursive just because it makes me feel better. A lot of people do print it, so that is fine. Limit as W approaches 6 of A, which would be equal to the limit as W approaches 6 of this expression, 12W minus W squared. And in this case, we can do something called direct substitution, where we can just plug stuff in. 12W minus W squared, that would be 12 times 6 minus 6 squared. 12 times 6, oh, my screen is all messed up on my calculator because I was playing a game with it, minus 36, that would give us 36, right? So we just have the limit of this area is 36. Again, don't worry, don't get too bogged down in trying to see that rectangle. What we're really concentrating on is this down here, limit. And we have a technical definition of a limit. Kind of weird to think about, but if f of x becomes arbitrarily close to a unique number L, as x approaches c from either side, the limit of f of x as x approaches c is L. This is written in the format that I just showed to you. So this probably looks really weird because you've never done it before, but what you really need to understand, LIM, underneath you put x arrow c of f of x equals L. This is read as the limit as x approaches c of f of x is equal to L. And our whole goal for today is to find L. What is it? So there's a couple ways that we can do it. There are good ways and there are bad ways. We are going to start with what we are going to call a bad way. Why would we start with a bad way? Because the bad way works every single time and it's not particularly difficult. So what we have here is, from the definition, a limit is if f of x becomes arbitrarily close to a unique number as x approaches c. So what we do is we set up a table of values. On this table of values, I like to put it vertically. I think your book puts it, no, your book puts it vertically as well. Yeah. We want to get arbitrarily close to 2. So we say when we have 2, when x is 2, f of x is, that's how you read a question mark, okay? So you might be saying, like, well, why don't we just do that mystical thing that I referenced earlier called direct substitution? And I'll get to that in just a little bit. But what we have here is we want to get arbitrarily close to 2. So something that is arbitrarily just means negligibly, almost right on it, as close as possible. So like I know 1.9 is close to 2, right? So here I can just go, and I'm using my calculator here because, whoopsies, that's not what I wanted to put in. I'm using my calculator just because I don't feel like calculating that by hand. 2 times 1.9 squared plus 3. Hey, that's 10.22, right? Okay. I can't see what this is getting to as I'm getting closer and closer to 2. So I get more arbitrarily close to 2. And more arbitrarily close to 2 is 1.99. So now I'm going to do the exact same thing. 2 times 1.9 squared. And there's a bunch of ways to cheat with your calculator and make it easier to put this stuff in. I will show you that in just a little bit. But here I've got 10.9202, right? Get closer, 1.999. Maybe that's even closer. Let's try this out. Insert another 9. We got 10.992002. Let's just put that as 10.992. And this really is a bad method because you don't know how close is close enough. I mean, I can see what this is getting closer to. I see that it's getting closer and closer to 11, right? So I'm going to stop here and say that I think that the limit as x approaches 2 of 2x squared plus 3 is equal to 11. Wait, no, I'm not. Because with a limit, I have to make sure that I approach the same value from both sides. And what do I mean by from both sides? I mean from what we would call the left, but below the target value, and from the right, above the target value. So here I need to go slightly bigger than 2. So like 2.1. I plug in 2.1. Okay, 2.1, get rid of those 9s. 11.82. Put in another 0.1 and maybe try 2.11. 2.11. 11.904, right? And I hope you guys see where I'm going with this one. Oh, I'm an idiot. 2.11 is not closer to 2 than 2.1. 2.01 is, and 2.001 is. I chose the wrong values. You have to be getting closer to 2. Man, I am so sorry that you guys had to sit through that. 2.01, that looks a lot better. It's getting closer. It was getting further and further away from 11, and I was just so scared that I was wrong. Anybody ever have that feeling in math? That never happens with anybody, does it? 2.001, 11.008002, but I'm just going 3 decimal places. Those of you who have me in class know that I always just go for 3 decimal places. So looking at this, I can see from both sides as the x value approaches 2, the f of x value looks like it's approaching 11. So I just get a feeling that the limit as x approaches 2 of 2x squared plus 3 is equal to 11. And again, you just do this until you get a feeling that it is entirely accurate. Now looking over here, notice that my approach value is 3. Oh, and some of you might be annoyed that you have to set up this table every single time. Yes, if you are using a table of values to approximate a limit, this is not calculating a limit, this is approximating a limit. But if you are using a table of values, you need to show the table of values. One of the things about math is you've got to show your work. So we've got at the x value of 3, f of x is equal to, I don't know, maybe she knows, but I don't know. All right, so I'm going to start with like 2.9, maybe go to 2.99, 2.999. Can you guys see how that's getting closer and closer to 3? And just like last time, let's make sure I don't screw this up this time. Start above 3, get closer to 3, get even closer to 3. And you know what happens if we can't see a trend when we get that close to 3? You get closer to 3 and you just keep looking for it. And sometimes there's okay, so some of you may have seen a movie called Mean Girls, and in Mean Girls there is a scene in which the actress that stars in Mean Girls says the limit does not exist. There are cases where the limit just does not exist, and I'll try to show you those later. Well, let's see. Oh, different function here. 1 minus 4 times 2.9. Okay. Negative 10.6. 2.99. Oh, it's a lot easier this time. Negative 10.96. Oh, man. You guys see what it's looking? I have positive 11 over here. This looks like it's getting closer to negative 11. I swear the answer is not always 11 or negative 11. But yeah, it looks like it's getting closer and closer to negative 11 from what we would call the left. Now we have to check out the right. So here, and if you guys can't understand why I'm saying left and right, look at a number line. Numbers that are lower than a number are to the left on a number line. Numbers that are bigger are to the right. So again, left up here, right down here. Technical terms, sorry. Negative 11.04. And I'm literally just plugging these numbers in here. 3.001, negative 11.004, and it should look from both the left and the right that I'm approaching the same value. And indeedly, diddly, doodly, it does. The limit as x approaches 3 of 1 minus 4x. I believe now it is negative 11. So that's what I think, all right? And actually, you can see, if I was to plug in 2 up here, I would have 2 times 4 plus 3. 2 times 4... 2 times 4... Woo, man, missed on multiplication there. 2 times 4 is 8, plus 3 is 11. Over here, if I plug in 3, 1 minus 4 times 3, that's 1 minus 12. 1 minus 12, that would be negative 11. So yeah, it does come to fruition that the direct substitution does work. Direct substitution does sometimes work, and I apologize right now for using that technical term of direct substitution. You'll never understand how to do it. Now, just to be clear, I want to point out direct substitution fails in this case. I see when I direct substitute, I have 0, and you really shouldn't be doing this because you don't know direct substitution yet, but I want to show you where direct substitution would fail. I get 0 over, well, I know 0 divided by anything is actually 0, right? No, not so true. 0 squared plus 0 gives me 0. This right here is something called an indeterminate form. This can literally be anything in the world. 0 divided by 0, I know you guys have been told in the past that you're never allowed to divide by 0. That's not entirely true. Your brains just weren't big enough to handle it at that point, so now we're telling you that you are big enough to handle this. Now, just to show you that 0 divided by 0 could literally be anything, I want to do a quick math problem up here for you. If I take 0 and multiply it by any number, say it with me, that equals 0! There we go. And if I solve this for a, doing something that you've been told you're not allowed to do, divide by 0, I get a is equal to 0 divided by 0. When we defined a was any number. So any number equals 0 divided by 0. What we call this is an indeterminate form. And there are other indeterminate forms, but we're not going to get into those. You will see indeterminate forms if you take calculus. Guaranteed, those will show up. when you get an indeterminate form, you need to do some further exploration on this limit. And this is a case where you would have to use a table of values because you have no other way of doing this right now. X, f of x, what's our target value? Our target value is 0. So we choose some numbers to the left of 0, some numbers to the right of 0. Something to the left of 0 is negative 0.1. Then maybe negative negative 0.01. Don't want to skip to 0.001 just yet. Negative 0.001 until we're close enough. And again, I don't know how close enough is, but yeah, I'm winging it right now. Down here to the right of 0 would be positive numbers. 0.1, 0.01, 0.001. All right? And notice the structure of my table of values. I like, as we get closer to 0, to like physically put the numbers closer to 0 just to make it easier to read. And now, yeah, I'm gonna use a calculator on this one. Alpha y equals fraction template. I've got negative 0.1 divided by negative 0.1 squared. Make sure you use those parentheses there. Plus 2 times negative 0.1. Okay, this is going to be a huge pain in the posterior to type in here, but we've got 0.526. All right, 3 decimal places, good enough for me. Okay, and here's where the pain in the posterior comes in. Change all of these to 0.01. Man, I really wish there was an easier way to type this in to my calculator. 0.503. Alright. 0.001, negative 0.001, and negative 0.001. Okay. So I'm thinking it's going to be 0.5, 1/2, but I don't know because I got to check from both sides. Remember, you have to make sure that it goes the same value on both sides. Okay, since these were identical to each other, I can just like scroll up doing my copy and paste and delete the negativos, right? Maybe that'll be a little bit, okay. At 0.1, I'm at 0.476. Okay, that's 6 of one, half dozen of the other. Which one do I want to do? If you've never heard that phrase before, go ask your parents what 6 of one, half dozen of the other means. Half dozen is half of a dozen. It's 6. Where was I? Oh, I was making a snarky comment and I forgot what I was doing. This is why I always tell my son not to be a smart aleck. Okay. So I can see from both the left and the right, it's getting to 0.5. So I've got the limit as x approaches 0 of x over x squared plus 2x. I'm going to say I think it is 1/2. All right. Now, because I don't feel like typing all that crap in over here, I'm just going to skip down to write Chihira, and I'm going to show you how to use your calculator in order to making your table of values a little bit easier. All right. So the way that we do this, and this will work with any Texas Instruments calculator. You can use a TI-83, TI-84, TI-89s. I know can do it. I just don't remember where. Okay, so the first thing you're going to have to do is switch your mode back into function mode, although I guess you could technically do this in polar mode because we're not actually using the grapher. We're using a numerical approximator here. So here I can just type in the function that I want to find the limit for. So the limit as x approaches 0 of x over x squared plus 2x. So I've got x over x squared plus 2x. All right. So one thing that people tend to screw up, they try to figure out how to type the limit into the calculator. I know there are some calculators out there. I think the TI-89 actually has limit notation in your calculator, but yeah, when you're doing this method, you don't actually type lim into your calculator. You type the function. All right. So next thing you have to do is change your table from the independent auto into ask. And the way to do that, you hit second window and it takes you to your table setup menu. Some of you, if you have me, might already have the independent variable listed as ask already. Make it ask. All right. And now if we go to second table, well, I've got some stuff in here, but you probably don't have anything in there. And I like to just clear all these out to figure out, or to just be able to see my table of values. And now I can actually use my calculator right here to make this table of values. I just plug in the x values into the x. I've got negative 0.1, I've got negative 0.01, negative 0.001, 0 was an error. And then from the other side, 0.001. Here's another thing that people tend to mess up here. They don't keep them in this order, and it's just really hard to read that table of values if you don't keep them in the proper order. And it looks like I've run out of room. So again, I can see coming from the left, it looks like I'm getting to 1/2. Let's just construct it from the right now. 0.001, 0.01, 0.1. And you can see from both the left and the right, it looks like it's approaching 1/2. It makes setting up your table of values like so much easier. Just to hammer through the second one, I can put x minus 2 over x squared minus 5x plus 6 and go to my table of values. Okay, I'm going to have to construct this over here just to keep... Sorry. I had a tickle in my throat, I swear. I think I'm healthy. Alright, so we got 2. Below 2, I got 1.9, 1.99, 1.999. From the right, I've got 2.1. Let's see if I don't screw this up again. 2.01, which is closer to 2 than 2.1. Remember, don't use 2.11. That just doesn't work. 2.001. And now, again, I've got the function plugged in here. You might have to do... Stop that. You might have to do left and right individually. Again, to clear them out, just hit delete. They'll clear out really quickly. Well, not really quickly. They take a couple seconds. 1.99, 1.999, and 2. 2 gives me an error. So I got negative 10/11ths, negative 100 101ths, negative 1000 1001ths, and let's see if I can change this from there we go. If you're kind of annoyed that you're getting fractions there, I mean, I can see this is getting closer and closer to -1, but if you can't, you can go into your menu, and this is only the people with the TI-84s, TI-83s, they automatically go to decimals. You can go down to where it says answers, click that over to decimal. I think that's going to fix it, yeah. And then you can see they're a little bit easier to read. Negative 0.909, negative 0.99, and maybe that's a little bit easier for you to see that it's getting closer and closer to -1. And again, we want to go from the other side as well. And added bonus for having decimals here, it looks like I'm going to be able to fit the whole table of values on here. Whoopsies, not 2.01, 2.1. And it looks like from both sides, and I'm annoyed at it as well, having to handwrite all of these things, but you do have to. Actually, I'm annoyed at this problem for so many other reasons, because again, this is a bad way to do this problem. I've got limit as x approaches 2 of x minus 2 over x squared minus 5x plus 6, I believe, is equal to -1. Alright? Again, it's approximately -1. I don't know for sure if it is. Actually, I do know for sure that it is -1 because I did it the correct way previously, and it is actually -1. Alright? So again, bad way to evaluate a limit. Horrible way to evaluate a limit. But sometimes you just don't have any other options. Like, you guys don't have any other options to find a limit. So now, here is something that screws with people. The limit of a function refers to the value that the function approaches, not the actual value, if any. So limit of a function, what we're looking here, that's our f of x, or our y coordinate on a graph. This is the height of the function, all right? All right? So now look down here. There's a bunch of uninteresting stuff that happens on this graph, and then there's one interesting thing that happens on this graph. Like over here, this is completely uninteresting. So they've got like the limit as x approaches, let's just say the limit as x approaches 0 of f of x. To make this a little bit easier to understand, I can list some stuff here for you. All right, so if I want to find the limit as x approaches 0 of f of x, I go over to my graph right here, and I can do a graphical approach to find this limit. This is your second method for evaluating limits. It's also kind of bad, but it's a little bit better than the numerical approximation. To find this, I go to where x is 0, and x means the lateral movement here. So I'm looking for where x is 0 right here. What's the what value does the function approach as I approach 0? Well, as I approach 0, it looks like the function is approaching a height of 1. So the limit as x approaches 0 of f of x is equal to 1. If I want to go to a different one, let's talk about the limit as x approaches 1 of f of x is equal to, well, when I'm going toward 1, it looks like I have a height of 1.5. So that would be 3/2. Or if I wanted to go something that might be easy to see as well, the limit as x approaches 3 of f of x, again at 3, what height does it look like I'm at? Okay, it looks like I'm at a height of 2. So that's equal to 2. Anybody notice which one I skipped? This one this bad boy right here. The limit as x approaches 2 of f of x. Okay, so I've been teaching calculus, trig pre-calc for darn near a decade, and this messes people up every single time I teach it to people, all right? So that's where we have something called a discontinuity. So I apologize for using such advanced terminology for you guys, but maybe you can figure out what a discontinuity is. You'll see that next year in calculus if you take calculus. Now, in order to evaluate the limit as x approaches 2 of f of x, I need to see what value the function is approaching, not the value that the function attains. I see a lot of people saying that the limit as x approaches 2 of f of x is 1. That is wrong. That is absolutely incorrect. What I do to find this limit, I come in from the left and I come in from the right, and I trace this graph and find out what am I getting, what height am I approaching as x approaches 2. I don't care about the instantaneous value, I care about what's approaching. So in this case, the limit as x approaches 2 of f of x is equal to 2. All right? And again, that is very difficult for some people to master. In fact, it's so difficult, it's a common problem that shows up in any calculus course. I think I see a problem like this on every single AP test that I've ever looked at, ever before. Looking at this, I got the limit as x approaches, okay, -3. That's 1. All right? Limit as x approaches -2 of f of x. Limit as x approaches -1 of f of x. Limit as x approaches 2 of f of x. I will point out that there are limits at other values here. They're just not interesting to us. Like, whenever you have a continuous function, it is just not interesting at all. Like right here, I don't want to figure out what the limit as x approaches -5 is. It's whatever height. It looks like at 0.2. The limit as x approaches 0 of f of x. That's looks like -0.6, right? The limit as x approaches 1 of f of x. Maybe about -1.9, and you can see some of my limitations on using the graphical method for evaluating a limit, because I just have to approximate that. It's like -0.9 or -1.9. Gross. Who likes to approximate stuff? But anyway, let's get back to over here. Limit as x approaches -3 of f of x. Again, I'm using the graphical method, so I have a pen in each hand, and, well, I have a pen and a pencil, right? So I'm coming in from the left, and as I go toward -3, and I stop where -3 is, well, just before -3, and I come in from the right, and I stop just before -3. Notice what happened to my pen and pencil here? They don't meet up. If you approach a different value from the left and a different value from the right, this limit does not exist, right? So the limit does not exist there. Looking at the limit as x approaches -2. Again, I want to surround, you want to get close to the target value. So like I wouldn't start out here if I'm going to -2, so like close to it. And I come in, and as I approach -2, see how they meet up? They meet up. Where they meet up, that is the limit value. So this is going to be equal to 0. And again, the value is the value of the function, so it's the height of the function at that point. Limit as x approaches -1, well, we see this dashed line, we know that that means a vertical asymptote, and as we come in from the left, it goes up. As we come in from the right, it goes up. So this is a value, technically I think the book wants you to just say does not exist right now, but we would call that infinity. So you have a limniscate right there. And the limit as x approaches 2, here again is what we call a removable discontinuity, because I really don't care about that black dot hanging out down there. I care about this right up here. Or, well, I don't even care about the open circle. What I care about is what value am I approaching as the x gets to 2, and it looks like, whoops, I forgot my negative, -0.5, right? So again, you're looking at the height as you approach, and just to show you, yeah, again, the book wants you to say D and E, but I trust you guys. You're kind of smart, right? All right. So conditions where limits do not exist. The limit of f of x as x approaches c does not exist if any of the following conditions is true. All right. So if f of x approaches a different number from the left side of c than it does from the right side of c, and you could see that is this first, the limit as x approaches -3 of f of x. That does not exist right there. So to see that on your calculator, you can actually graph this right down here. The limit as x approaches 0 of 2 times the absolute value of x over x. Just to show you guys what that looks like. Put in a fraction. Again, we know that we're not actually putting in lim into our calculator. We're using our calculator as a tool. 2 abs x over x. And we can graph it. You can see there's that discontinuity here. From the left, the graph looks like it's at -2. From the right, it looks at it like it's at +2. -2 not equal +2. So, yikes. You can see that in your table of values. Since we're approaching 0, we can plug in -0.1, -0.001, -0.01, -0.001, 0, 0.001, 0.01, 0.1, and you can see from the left, the above region is -2, from the right is +2. Another one we have is f of x increases or decreases without bound as x approaches c. So this is the case where I kind of take issue with how the book is describing this. They're basically saying anytime you have a vertical asymptote, the limit does not exist. There are cases where the limit does exist at infinity or negative infinity, but just to be clear on what I'm talking about here, this is the second case here. So we can plug this in, 3 over x to the 4th, and I mean, you guys know from this year that if I plug in 0 down there, I'm going to get 3 divided by 0. That's no bueno. So I can actually see that at 0, I'm going to have that vertical asymptote. And since technically from the left and the right, they both go up, this limit does exist at infinity. But right now, you're okay just saying D and E for that. And to show you what that would look like in the calculator, since I'm approaching 0 on this one again, I can use the exact same table of values, and you can see as I get closer and closer to 0, they're just getting bigger and bigger. I mean, you've got 3 times 10 to the 8th. That's big. 3 times 10 to the 12th. That's even bigger. So yeah, it's just increasing without bound. And the last one is really difficult to see. It's an oscillating, what we call an oscillating discontinuity. And you don't really need to worry about that one too much. We'll get into it next year, but what you can see here is it just kind of goes psycho as you get closer and closer to 0. You can zoom in on that to see that as you zoom in more and more, it just oscillates more and more and more. Again, as a calculus teacher, I can tell you this comes up in calculus. It's the hardest one to see, but you know, it exists still. So again, 3 cases. Ooh, now we get into the first good method of evaluating a limit. It also happens to be, I think, the easiest method of evaluating a limit. The bad part about it is, I know you guys are thinking, like, what if it's the easiest and the best, why didn't you show us first? It's because it doesn't always work, and it is called direct substitution. So that is when the limit as x approaches c of f of x is equal to f of c. It's actually the very definition of a continuous function. If direct substitution works, then the function is continuous. So we have a couple of properties here. If you're finding the limit as x approaches c of b, that's just b. Limit as x approaches c of x, that's just c. Limit as x approaches c of x to the n, that is c to the nth. Limit as x approaches c of the nth root of x is equal to the nth root of c as long as n is even and c is greater than 0. So that looks like a lot of stuff here, but b and c are just numbers. Really, when we have the limit as x approaches c of a number, the number is the answer. Here, x approaches c, you plug c in for x. Same thing here. Change x to c. Alright? So I'm going to show you guys these. They're not hard whatsoever. Maybe pause for a second, try them out, and then pick back up right here. Like here, I've got the limit as x approaches 4 of 2. Well, I plug 4 in for all x's. There are no x's. This is 2. Limit as x approaches 0 of e. I plug in 0 for all the x's. No x's? Okay, this answer is the number e. Over here, I plug in 1 for all of the x's. This becomes the square root of 1. Should we leave it as the square root of 1? You could, but I don't want to, because I know what the square root of 1 is. It's 1. Over here, I've got limit as x approaches 2 of x squared. Okay, that becomes 2 squared. Do I know what 2 squared is? Yes. It's 4. Change all x's to 27 over here for the limit as x approaches 27 of the cube root of x. Cube root of 27. If I need to, I can use my calculator for this one. But I happen to know that 3 cubed is 27, so the cube root of 27 is 3. Over here, change all x's to negative 3. Make sure you use parentheses. Negative 3 squared. 9. Okay, this one I didn't really tell you how to do, but it's on the page with direct substitution. So to ruin it for you, you just direct substitute. Sine of pi. Bust out your unit circle. I know pi is right over here. I know that that ordered pair is going to have to be negative 1, 0. Okay, the y value is 0. Boom. There we go. Direct substitution, best method to use if it works. And the times I'm emphasizing if it works, where it doesn't work is when you get an indeterminate form. So if you get 0 over 0, you have to look for other techniques. If you do not get 0 over 0, direct substitution works. Well, okay, or divide by 0. Basically, if 0 is in the denominator, it doesn't work. But we're not going to do any any numbers other than 0 divided by 0. So properties of limits, here are some things that just open up the door to direct substitution. If b and c are real numbers, n is a positive integer, let f and g be functions with the following limits. Limit as x approaches c of f of x equals L, and limit as x approaches c of g of x equal k. If you multiply a function by a scalar multiple, you multiply the limit by the scalar multiple, okay? If you want to add two functions together and take their limit at the same value, you add the limit values together. Multiplying two functions together, you just multiply the two values of the limits together. Quotient, as long as the denominator is not 0, you just divide the limits, and same thing with power. You just do raise it to a power. All this looks really confusing. I know it's not. It basically just says if it works, plug in. All right. And that's this too. This basically says, if you have a polynomial, direct substitution works. Period. If you have a rational function, so if you have polynomial divided by polynomial, as long as the denominator not 0, direct substitution works. So all of those theorems can be summarized in try direct substitution first. If it works, that's your answer. If it don't work, try something else. Alright? And the something else's that you can try as of right now, you can try the graphical approach or you can try the numerical approach. There's nothing else that you know of at this stage in the game. So I thought I'd give you guys enough time to pause the video and then pick it back up so that you can see all this stuff right here. So finding a whole bunch of limits. Okay, change all of your x's to -1. There are none. The answer is 5. Alright, so I hope I'm not going too quickly for you guys here. Take -5/2, plug it in right here. You've got -5/2 plus 2. And you might be annoyed that you have to put this much work. Whatever, it's less work than making the table. This would be equal to, so +5/2 plus 4/2, 9/2. Alright? 4.5 if you want it that way. Over here, okay, so if it works, direct substitution is good. Let's see if it works. 2 cubed minus 2 squared minus 4. 8 minus 4. 4. Minus 4. 0. Oh crap, I told you if you had... No, I didn't tell you if you had 0 that it doesn't work. I said if you have 0 in the denominator, D sub don't work. 0's in the numerator, so the answer is just 0. Over here, I don't think I have enough room for this. -1 squared over 2 plus 2 times 1 plus 4. Let's see. -1/2 plus 2, so 3/2 plus 8/2, 11/2. Would it be acceptable for you to put 5.5? Sure, whatever. I like fractions. They're cool, right? Down here, I've got negative square root of 3 plus 3. Okay, 3 plus 3 is 6. Does anybody know what the square root of 6 is? This guy does. But since I'm going for exact values here, direct substitution gives me the exact value of the limit. This would be negative square root of 6. Going over here, negative square root of 2 times 3/2 plus 4. Okay, 2 times 3/2, 3 plus 4, 7. Negative root 7, right? Now, to cheat on this one, usually whenever I see a fraction, because if I have a denominator of 0, I can't use direct substitution. Usually, what I do, if you want to be like me when you grow up, let's not forget that negative there, I do the denominator first. Oops. I want to make that 1, right? So if it's 0, I just give up on this method, and I go for some other method. 1 squared, 1 minus 6, so -5. -5 plus 8 gives me 3. So I've got negative something over 3. And honestly, if I did get 0, I would check out the numerator to see if it was 0 or some other integer. And then for the numerator, I've got 1 minus 4. Okay, so that's -3. So -3 divided by 3. Okay, that gives me 1. All right. Oh my gosh. I don't feel like messing around with these fractions here. Who made up these problems? Okay, so do we want to cheap out on this one? Yeah? Okay. Nobody tell anyone that I did this. Alright? So -3/2 minus 3 over 3/2 squared plus 3/2 plus 1. Okay. And I already told you guys I like fractions, so I'm going to switch that to a fraction. Hey, there we go. What? No, I totally did this by hand. Of course I did. Yeah, 100%. I think, didn't we already do this one? Limit as x approaches pi of sine. Yeah, that was just 0, right? Yeah, we actually did that in the last problem. to cosine of 3 pi over 4. Okay, so cosine of 3 pi over 4. I know 3 pi over 4 is halfway through the second quadrant. You guys see? Oh, you guys can't even see my graph work down there. I happen to know that the halfway point is the root 2 over 2 comma root 2 over 2. Since it's in the second quadrant, that's got to be negative. So this is going to be 2 times negative root 2 over 2, which gives me a value of negative root 2. Double check answers. Remember, if you don't want to do direct substitution, you really should, because it is much easier than the other methods, but you can always just graph it and find the value. Like if I wanted to do number 8, I could have just plugged in negative x minus 3 over x squared plus x plus 1, and I could have gone over to my graph. Ooh, man, zoom windows all messed up there. Come on, graph, you fool. I could have gone to x being 3 halves, so I like to go to my trace to see that. 3 halves, 1.5, 1.5, okay, negative 0.938. But again, using the graph is going to be not as accurate. I don't know if I'd ever be able to get negative 18/19 on that one. I mean, maybe if I went to 1.5 and then did y 4. Let's see if that, so I could cheat it and use that. But hey. Now, welcome to the world of limits. There's some problems there. I'll probably put some other stuff on the website as well. Yeah, this was fun, guys.